Hello there, and welcome back. In this video, we're going to continue our discussion of special probability mass functions and introduce two more to our list. So far, we've discussed the Bernoulli distribution, the uniform distribution, and the geometric distribution. In terms of fun applications, I think out of these three, the geometric one has the most variety in terms of fun applications that can be applied. But of course, the other two are important and have special applications associated with them as well. So let's just focus on the geometric distribution for just a moment. So what the geometric distribution does is it focuses on probability of events where the event is of the structure failure, 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 all the way out to one particular success. Now in particular, this is a particular order of failures and one success, right? In particular, it's all of these being failures and one of them being success. That's really different from saying, out of 10 trials, what is the probability that one of them is a success, right? So let's just write those down. So question variation 1. So what is the probability that the last of 10 trials is a success and the other ones and the other failures. And question 2 is the probability that exactly 1 of 10 is a success and the other failures, right? So in terms of the difference between the two, and one can easily find the connection between the two. So we actually already know how to find the probability of exactly one failure where the last one is a success and the other ones are failures, because that's just going to be equal to the probability of failure to the power of, let's assume we want to find the probability that we have x, right? So the geometric says that there's going to be x minus 1 failures times the probability of success. So that's either the last one being a success, or the first one being a success, or the middle one being a success, and so on. But that's not any one of them, right? It's a particular one. So in terms of this other one, that means we're interested in the event, for example, failure, failure. Let's just do 3 trials. So that means we're interested in either failure, failure, success, or failure, success, failure, or success, failure, failure, right? So that would be the n is equal to 3 case, right? Not necessarily the n is equal to 10 case, right? Notice that these events are mutually exclusive, so that's going to be the probability of failure, failure, success, plus the probability of failure, success, failure, plus the probability of success, failure, failure, since they're mutually exclusive events, right? And then each of these events are exactly the type of event that this first problem was solving, right? In particular, this is our geometric, and these are also equivalent, I guess you could call it, geometric distributions, right? At least in its functional representation. So of course we know how to find each of them, and how many are there where there's exactly 3 of them, but in particular it's not just 3, but it's 3 choose 1, because notice that we're just doing rearrangements of 3 objects where we have 1 success and 2 failures in that rearrangement, right? And we know that that's just the same as C3, 1. So that means the probability of any one of these 10 being a success is just going to be equal to C3, 1 multiplied by the probability of failure to the power of 2 times the probability of success to the power of 1. And then you can easily extend this to 1 out of 10 just by changing that to 10. So that would go to 10. This would go to 9 because we want 9 failures and we want 1 success, so that would stay the same, right? So that would be how we would find that. So how would another problem look like? So let's assume we don't want 1 success. What if we want many successes? So what we're going to do is so let's just define this random variable. Let's go ahead and do it. So this is going to be called a binomial random variable, which is going to be modeled by a binomial distribution or a binomial probability mass function. So it goes like this. So suppose you conduct a sequence of n independent Bernoulli trials, so either can be success or failure, each with probability, let's call it lowercase p, and we're going to let x, so this is going to be my binomial random variable, be the number of successes in that sequence. Right? So let's look at just a quick example. Suppose we let n be equal to 5, and let's find the probability that x is equal to 4. So what would that look like if we didn't have a little shortcut formula to go by? So that's the probability that x is equal to 4 is going to be equal to the probability of success, 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 failure, success. So that's 1. Or we could have success, success, failure, success, success. Or we could have success, failure, success, success, success. Or we could have failure, success, 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 success. Or the last one, success, 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 and failure. So all of these, 1, 2, 3, 4, and 5, are all mutually exclusive events. So we can just add them. And how many events do we have? So we're going to have 5 choose 4 of them, right? Because we're counting the number of rearrangements of these objects. And then we can just choose one of them. It doesn't really matter what it is, right? So let's choose this last one, just without loss of generality. So that's the probability of success, 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 and failure. And of course, there's intersections in between each of them, but that's just assumed. So keep in mind, we're assuming that each of these baby events are independent events. So we can do the product of each of their individual probabilities. So that's going to be equal to 5 choose 4 times the probability of failure to the power of, let's do 5 minus 4 because that's 1, because I'm going to be building into a pattern here. And then times the probability of success to the power of 4, right? Because we're focusing on the successes, right? So there's 4, there's 4, there's 4, there's 4, so that's my x value. And then here, these numbers, that corresponds to my number m. So we can generalize this very easily. So if we have n independent Bernoulli trials, then the probability that we get x successes is going to be n choose x times the probability of failure to the number of failures times the probability of success to the power of the number of successes. So this is what we refer to as the binomial probability mass function. So keep in mind, what is the domain of this function? So it is possible to have 0 successes in a sequence. So that means the domain of this function, p of x, is going to be the set 0, 1, 2, 3, 4, all the way down to n, because all of them could technically be a success. Now let us look at a particular application where we might be able to use the binomial probability mass function to solve it. Suppose you have a population for which 24% of them are sick with some virus, and you take a simple random sample of 20 people. What is the probability that exactly 15 of those 20 people are sick? So let's just take a look at what we have here. So we have a population for which 24% of them are sick. So if we randomly select one person from this population, there's a 24% chance that that person is sick, assuming we're taking a random person, of course. So what we have here is that the probability of success for a particular event is going to be equal to 0.24, which means that the probability of failure, some people usually represent this as Q, is going to be 1 minus 0.24, which is going to be equal to 0.76. So that's the probability of failure. So failure, success. So from here, what can we do? So what we're doing is we're taking a simple random sample of 20 people. So that means the sample size is going to be equal to 20. And then we're interested in the probability that we get exactly 15 of them. It doesn't mandate a particular order, for example, the first 15, the last 15, or some rearrangement that we're interested in. We just care that exactly 15 of them any of them are sick, right? So that would be a combination. So since all of them are independent, let's say, in terms of their sickness, let's assume, therefore we can use the probability mass function associated to a binomial random variable. So let x be the number of people that are sick in my sample, right? So what is the probability that x is going to be equal to exactly 15? So I'm focusing on 15 sick people out of 20, and I don't really care the order, so I'm using a combination there. Then we have the probability of failure to the number of failures, which is going to be 20 minus 15, right? Because we're focusing on 15 sick people, that means 20 minus 15 of them, which is 5, are not sick, right? Because the probability that you're sick is 24%, which is the probability that you're not sick is 76%. And then times the probability that you are sick to the power of the number of sick people in my sample that I'm interested in observing. So of course, let's just break this formula down and write it down. Why not? So this is the number of rearrangements of sick people. This right here is the probability of failure. This right here is going to be the probability of success. This exponent here is the number of not sick people. And this is the number of sick people in my simple random sample for both, of course. Okay. So, of course, you have to remember, what do I mean by probability of failure? That's the probability of not sick, and this is the probability of sick. So make sure you have your definitions for your events squared away because you don't want them to be confused with each other. Okay, so now that we have understood what this formula is, so what do we have? So we have Px of 15 is going to be equal to 20 choose 15 times 0.76 to the power of 5 times 0.24 to the power of 15, which is approximately equal to 0.123451999. Okay? Very important, this is not the same as 0. Okay? Because 0 means impossible. This is just approximately equal to 0. Even just writing this implies that there may be non-zero digits after it, but do not just write 0 if your number is small. You may even want to use scientific notation. For example, this is 1.94 times 10 to the negative power of 1, 2, 3, 4, 5, 6. Right? So that would be an equivalent way of writing this answer in case you don't want to imply that this particular event that we're talking about is impossible. That's very important. So another type of problem that you might be wanting to know is the probability that maybe more than 15 or more than 3 or more than 6 or at most 5 or less than 3 or these types of problems you can also solve in a very direct way. So let's assume we're working with the same exact problem. So what's the probability that x is, so we're not going to be using the probability mass function quite yet. So what is the probability that capital X has a value greater than or equal to 6? So that means we want to plug in 6, we want to plug in 7, we want to plug in 8, all the way up to 20, because that means all of the people are sick. So what is the probability that at least 6 in our simple random sample are 6. That's what this means, right? That's different than more than 6, right? So more than 6 will not include 6. So that's important to know the difference between them. At least, at most, less than, or, those types of words. Make sure you know the difference. So we can write this in summation notation if you want, or you can just find these probabilities manually one by one. That's okay. Or you can just write this in summation notation. So this is the sum from x is equal to 6 to 20. And that's going to be equal to something. So what is that? So that's just going to be the combination of 20 choose x times 1 minus p to the 20 minus x times p to the power of x. And what was that? What was p and what was 1 minus p? So that's going to be the sum from x is equal to 6 to 20 of 20 choose x, because that's going to change for each value. And then we're going to have 0.76 to the power of 20 minus x times 0.24 to the power of x. So once you do this summation out, which you could do one by one, or if you have software to help you, then this will just come out to approximately 0.3427, assume that I did it correctly, right? So that is how you can solve problems like this. Now let's just look at one other thing that might help you gain some intuition as to, is this probability right, how to interpret this probability, and so on. And that's from the graph of the probability mass function associated to a binomial random variable. So there's going to be three different types of graphs for binomial random variables. So keep in mind the smallest value is going to be 0 and the largest value is going to be m. So if you have a data point or a discrete distribution that looks like this, so notice that this is a skewed right distribution, Notice that most of my probabilities are located on the left-hand side. So this type of graph is always going to be associated to a binomial distribution where the probability of success is less than 0.5. And similarly, if you have in there, 0 there, and we can use n divided by 2, the mid-range, as a middle comparison. So if you have a distribution like this, it's always going to have this curvy, skewed bell-shaped pattern, which is interesting. So here we have a skewed left distribution. This is always going to be associated to a probability of success being greater than 0.5. And finally, you might be able to guess this last one. Again, n over 2 is there, n is there, and 0 is there. If you have a distribution like this, then this is always going to be a symmetric distribution, which is always going to be associated to a probability that is equal to or approximately equal to 0.5. So these three types of graphs can sort of give you an insight of where the most likelihood of values are going to be equal to, and associated as, the numbers of values in your samples that you're actually referencing with respect to n over 2, and 0. Now, since x is a random variable, it's going to have formulas for its expected value. So if x is binomial, then we have an expected value formula. The expected value of a binomial random variable is going to be equal to n, the size of the sample, times the probability of success. And the variance of that random variable is going to be n times p times 1 minus p. So you might ask, where do these two formulas come from? I'll go through the proof of the expected value formula in just a couple seconds, and I'll sketch out the proof for the variance formula too. I'm going to change the color background and of course not speak, with a little bit of relaxing music in case you want to watch the proof, or you can just skip to where the screen background turns back to yellow, so we can pick up where we leave this discussion off and start discussing a couple other applications in the next distribution that we're going to be interested in. Now let us look at a brief example on how we can use the expected value formula for a binomial random variable. Let us assume you have a population for which 71% of them are stressed every single day of their week. If you select a simple random sample of 327 people, what is the expected number of people in your sample that was stressed every day of last week? So a couple things here. So we're selecting a sample from a population for which the probability is 71% that a single person selected will be stressed every day of their week. So this is going to be our probability of success. Another thing we need to assume is that each of the people in our sample and also our population must be independent of each other with respect to the stress level for which we are measuring. Since that's not given, let us just assume, since we do not have any information to suggest otherwise, that they are dependent on each other. Also, our simple random sample is of size 327, so let us assume that x is the number of people, so the number of people in our sample that was stressed every day of last week. So if we're assuming that the people in the sample are independent of each other, and we have a probability of success, and n is the sample size, and we're assuming that x is the number of successes in that particular sample, then we have that x is a binomial random variable. If that is the case, then the expected value of that binomial random variable always is going to be equal to n times p, which is going to be equal to n, which is going to be 327, times the probability of success, which is 0.71, which from the interpretation is just 71% of our sample, right? So it technically makes sense. So that's going to be approximately equal to 231.17. So we should expect somewhere around 231 people out of our 327 to be stressed. If we do get a number that is significantly smaller than 231, or a sample that is significantly larger than 231, then it's most likely associated to the fact that this sample was not actually a simple random sample. So that's one of the things that you can test and see, is this a biased sample or not, or something like that. Now, one note that I do want to mention on the binomial random variable, so an important note, is that the domain of the PMF for a binomial random variable is equal to 0, 1, 2, 3, 4, all the way up to, say, n, where n is finite. So let's assume you want to take a test. What is the probability that you succeed, 6 out of 10 times? The binomial distribution cannot be applied where the number of attempts is infinite. That is, you can try infinitely amount of times. So one question is, can you modify the binomial probability distribution in order to account for this possible desire for studying? So here's our guiding question here. What if, why aren't you writing? What if you want to attempt things indefinitely? So we are assuming still that each of these trials are independent of each other and we have a fixed probability of success, p. So what we can do is we can slightly modify the probability mass function for a binomial random variable, right? So let's look at that. So we have our combination in front, and then we have 1 minus p to the m minus x times p to the x. So what we're going to do is we're going to define a new variable, and this is going to be clear later why we want to do this. So we're going to define p to be equal to lambda over n. So what exactly is p equal to lambda over n? So remember, p corresponds to the probability of success. Lambda over n looks like an empirical or a theoretical probability definition, right? So it looks like, the number of trials and the number of successes in that particular sample that we have, right? So if we rearrange this formula just a little bit, we're going to have lambda is equal to n times p. So remember what n times p is. N times p was the expected value for a binomial random variable. So lambda by itself represents the average number of successes in a sample of size m, right? So this little substitution of p equals lambda over n definitely has a lot of interesting things going on with it. It has two important observations. So what we're going to do is we're just going to replace that into our definition everywhere we see p, and we'll see what that comes out to. So we're going to have Pxx is going to be equal to n factorial x factorial times n minus x factorial, and then we're going to have 1 minus lambda over n to the n minus x times lambda over n to the power of x. So what I'm going to do now is I'm just going to rearrange this formula just a tad bit. And if you're not strong in algebra, you can maybe ignore the step, or if you're strong in algebra, maybe you can prove to yourself that this is indeed the case. But if you rearrange this formula, you're going to have 1 minus lambda over n to the power of m times lambda to the power of x over x factorial. So what is this? So this is 1 minus lambda over n, so that's this piece. Lambda over x factorial, so there's our lambda x, there's our x factorial, so everything's accounted for, at least almost. And then everything else I want to put on the end. So we're going to have n factorial all over n minus x factorial, so I'm taking care of those two things. I'm still left with something with this 1 minus lambda over n, and also an n to the x power there. So let's just throw them down here. So 1 over lambda to the n to the power of x, because it's negative x, so when we reciprocate it becomes positive, and n to the x, right? And again, if you're just focusing on practical purposes, you don't need to memorize this, but then we get this expression. So what do we want? We want n to be as large as possible, arbitrarily large, right? So what we're going to do is we're going to take the limit as n goes to infinity of this distribution. So once we take the limit, this is a new distribution, so keep that in mind. So this is a new random variable. All right, this is going to be a new random variable. So what random variable is it going to be? So this is going to be equal to the limit as n goes to infinity of 1 minus lambda over n to the n times lambda to the x over x factorial. I'm going to just focus on that piece. Actually, I don't need to focus on that second piece because it doesn't even have n in it. And then times the limit as n goes to infinity of this thing. N factorial, n minus x factorial, 1 minus lambda over n to the x, and n to the x. All right, so I leave it as an exercise for you calculus lovers that this will go to 1, and that this limit here will go to e to the minus lambda. So once we got all that situated, we're just going to be left with e to the minus lambda times lambda to the x over x factorial times 1. So I'm just going to forget that times 1 thing, and I'm just left with this very cute little distribution. Right? So who is this new character? So this new character is known as the Poisson distribution. Poisson distribution. Right, and x is known as a Poisson random variable. So Px of x is equal to e to the minus lambda times lambda to the x all over x factorial. Right, so x is going to be a Poisson random variable. It has this property. So what is the domain of this new function? This is going to be equal to 0, 1, 2, 3, and so on. So you can technically have 5 million successes and not have to worry about large numbers with the binomial distribution for this type of thing, which is actually really, really handy. Since it's a random variable, it's going to have an expected value, right? So the expected value is going to be equal to lambda, and the variance of this Poisson random variable also equals lambda. Very, very interesting. It is the one of the only probability mass functions for which the expected value and the variance are equal to the same exact number always, right? And that is equal to the average amount of successes in some interval of interest, right? Now, how do you prove this type of thing? Of course, I'm going to show you. I'm going to change the screen background color and give you some peaceful music to listen to while I go through it. Enjoy. Now that we know a few things about the Poisson distribution and its relation to the binomial distribution, let us look at a particular example and determine whether the Poisson or the binomial distribution is more appropriate to solve this problem. So let's look at these wordings in very close detail. So let us assume that every day, on average, 27.4 people go to a particular restaurant between 12 p.m. and 1 p.m. for lunch. So off the surface, we have 27.4 people going to a particular restaurant every single day. So this either could be lambda for the Poisson distribution, or it could be n times p for the binomial distribution. If you choose a random day, what is the probability that exactly 20 of them, so we're looking for x is equal to 20 for some particular probability mass function, assuming that they come between the restaurant between 12 p.m. and 1 p.m. So keep in mind, this average must be the same exact interval for what you're interested in, unless you know for sure that the distribution across 12 to 1 is the same as the distribution from 1 to 2 versus the distribution from 7 to 8 p.m. or something like that. Typically in practice they are not, so you would have to have given information or assume that they are equal if it says you're allowed to do so, right? So which distribution should we use? Should we be using the Poisson distribution or the binomial distribution? So notice here we do not have a sample size n in order to find this probability p, and that's a problem. So technically speaking, is there an upper bound for the number of people that can visit this restaurant between 12 p.m. and 1 p.m.? Typically speaking, the answer is yes, but we do not know the maximum capabilities in terms of how many people can fit in this restaurant. So as far as we are concerned, we need to assume that the upper bound is infinite, and then use the Poisson distribution for this particular scenario. Now keep in mind the distribution does have the same exact type of shape as the binomial distribution, so eventually it does tail off to practically zero. So even though it is not bounded above, there is a value for which the probability is practically 10 to the minus 10, or whatever value here. So you can sort of treat this as the number 0 and call whatever value that is n and then use the binomial. But technically, why not just use the Poisson distribution if all of those values after that particular number are quote unquote practically 0, right? So let's just use the Poisson distribution, and let's solve this very quickly. All right, so we're assuming that the people are independent. That's also a very important thing, else we couldn't use binomial or Poisson for this. So that means you're not allowed to bring like a group of 10 friends to this restaurant because that means one is completely dependent on arriving with the others, right? So if we're assuming this is a Poisson distribution, then we have lambda is equal to 27.4, and that means the probability mass function Poisson random variable is going to be equal to e to the minus lambda times lambda to the power of x all over x factorial, right? So this would typically need to be done in a calculator. 20 factorial is a really big number, very, very big. So if that's the case, then we have some rounding issues if you do this by hand. But if you actually do this out in a calculator, you should get this is approximately equal to 0.0295, right? So that gives us the probability that exactly 20 people arriving in this restaurant is approximately 3%. Now, let's just close out this video with a particular example that is also commonly discussed. So what is the probability that more than 24 people come into this restaurant between 12 p.m. and 1 p.m.? Now remember, what is this from the probability mass function perspective? So that's going to be equal to the probability of 25 plus the probability of 26 plus the probability of 27. Now, unlike the binomial distribution, this is not bounded above, right? There's always going to be some non-zero probability values up there. Even though they're approximately 0 eventually, we can't just throw them out because there's infinitely many of them. So how can we get a good value for this? Well, keep in mind the Poisson and binomial distribution are both bounded below by 0. So we can always approach this type of problem, either greater or greater than or equal to, via complements. Because this is just going to be equal to 1 minus the complement, which is going to be probability that x is less than or equal to 24, which is going to be 1 minus the probability that x is equal to 0, plus the probability that x is equal to 1, plus the probability that x is equal to 2, all the way up to the probability that x is equal to 24, and make sure that you're not including one in the other because they are complements and should not have any overlap. So if we want to write this in summation notation, how would we do that? So we'll find the probability that x is greater than 24. So this is going to be equal to 1 minus, so this is going to be the sum from x is equal to 0 to 24 of px of little x, right? Which is going to be equal to 1 minus the sum from x is equal to 0 to 24 of e to the minus 27.4, that's our lambda value, times 27.4 to the power of x, all over x factorial, and you let that sum run across those values of x's from 0 to 24, and you're going to find that's approximately equal to 1 minus 0.2975, which then of course comes out to approximately 7025. So what is the probability that more than 24 people show up to the restaurant between 12 p.m. and 1 p.m.? That is going to be approximately 70% chance. So these two distributions, the binomial distribution, the Poisson distribution, several applications for which you can use these distributions for. So in the upcoming video, we'll introduce 3 other special probability mass functions that can also widen the horizon in terms of the applications for which you can use for solving probability problems, and of course a lot more after that. So I hope to see you there, and I hope you take care. See you.